Hi everybody, it's Mr. DeCrane, and we're going to do a lesson on transforming basic sine and cosine functions. This may not seem like a terribly exciting thing, but we want to be able to change those basic graphs into something like this. It has lots of applications, for example, modeling the number of daylight hours in a city, or the high and low tides, or even the amount of CO2 produced by a volcano like Mauna Loa. So before we get started, what I'd like you to do is go back and talk to a partner or write a note to yourself about the period and the amplitude of our basic sine and cosine functions. Review what amplitude means and what period means, and write down the amplitude and period of sine and cosine. Pause the video and do that. I'll wait, honest. Okay, I'm hoping that you remembered that amplitude is half the distance between the minimum and the maximum values of the function. So when we're talking about the sine and cosine functions, that's really how high the graph is above and below the axis. So for both graphs, we go 1 unit up and 1 unit down from the x-axis, the horizontal axis. So our amplitude for both these graphs is 1. Remember, that's a distance. Similarly, the period is how long it takes to go through one complete cycle. One complete cycle of the cosine graph looks like this, and that total distance that we travel in that period, in that one cycle, is 2 pi. The same thing happens with the sine curve. One complete period of the sine curve looks like this, and so the total distance that we travel from the beginning to the end of that sine curve is also 2 pi, so the period on that graph is 2 pi. And that's the same for both graphs, and we'll see that's going to be really important as we go on. So how do we transform that? If we were going to change these graphs around and stretch them a little bit, today we'll talk about the stretches. So first of all, let's go back to our basic ideas about vertical stretches, and let's think about our old friend y equals x squared. And what I'd like to do is think about how do we change that into y equals 2x squared. So again, pause the video and talk to a partner about what changes are made to the graph and the table when we look at y equals 2x squared. Again, I'll wait. Okay, so hopefully you remember that when we do y equals 2x squared, the new y values are all doubled from the old ones. So that would be 18, and this would be 8, and that's 2, so that's still 0, 2, 8, and 18. And when we look at the graph, all the y values double, so they get stretched up a bit, and the graph is a lot steeper than before. Get it on this one too, 8, there we go. So it makes the graph a lot steeper. So let's talk about what happens when we do that to our basic sine curve. Here's y equals sine of x, and what I'd like to do is look at y equals 3 times the sine of x. And since it's 3 times the old y values, our new y values are just 3 times as big. So here at pi halves, where the y value is 1, we now end up with the point, we're looking at 3 sine of x for the y values. At pi halves, we were at 1, so we're now at 3. And at pi, we started out at 0 on the graph, so that's going to stay at 0 because 0 times 3 is 3. Here at 3 halves of pi, we're at -1, so when we multiply it by 3, we get -3, and then, so we're down here, and then back at 2 pi, we're at 0 again. And in between, there's a couple of values that are really important to notice. This point right here at pi sixths is at 1/2. When you multiply it by 3, we get 3 halves. At 5 pi sixths, we're at half, so again we go to 3 halves. Here at 7 pi sixths, or 7/6 of pi, the y value is -1/2. Multiplied by 3, we end up at -3 halves. And over here at 11/6 of pi, we're at -1/2, so we end up again at -3 halves. And if we connect up those points, we end up with this stretched sine curve. So that's one period. I can keep going and finish off the whole curve. I'm going to label a couple of extra points in here so I can make it pretty smooth. There we go. And the same thing on the other side. So that's the graph of y equals 3 sine of x. what I'd like you to do is talk to a partner and see if you can predict what the graph of y equals 1/2 sine of x looks like. Again, pause the video, decide what it's going to look like, and then actually go ahead and graph it, and I'll check back with you in just a few moments. Pause the video. Okay, so when we graph y equals 1/2 sine of x, that means we only go up a half off the axis, and so the graph ends up looking more like this. That was not very good. Let me try that one again. I should be going through the origin. There we go. And that's y equals 1/2 sine of x. Now, an important thing to notice here is that the height off the axis for our original graph here is 1, and the amplitude is 1. On our transformed one, y equals 3 sine x, notice that we're 3 above the axis and below the axis. So our amplitude on that first transformed sine graph is going to be 3, and on the second one, we only went up, we only went up half a unit off the axis as our maximum or minimum. So there our amplitude is a half. And it's not coincidence that the amplitude matches that multiplier. That actually shows up in the equation very nicely. What I'd like you to do is now do it to cosine. And so I want you to take a graph of cosine, and I want you to show y equals 4 cosine of x. And I also want you to show y equals 3/2 cosine x. Again, pause the video, talk to a partner, discuss what that's going to look like, and then actually make the graph. I'll check back with you in a minute. Okay, so here's the graph of y equals 4 cosine x and y equals 3/2 cosine x. And again, pay attention to the amplitudes. The amplitude on this blue graph, y equals 4 cosine x, is 4. And the amplitude on the red graph, y equals 3/2 cosine x, the amplitude is 3/2. And it's important to note that the key points here where the graph crosses the x-axis don't change at all when you just stretch it vertically. Those stay the same. Those are fixed points on vertical stretches. Moving on to horizontal stretches, this one may take a little bit more thinking because we're not used to looking at horizontal stretches quite as much. Most of the graphs we've looked at up to this point and into algebra, we've only looked at vertical stretches. So here we got to look at horizontal stretches a little bit more. So think back to your basic graph of y equals sine x. The input to this is an angle, and the output is that ratio. So when the angle is 0, and I'm talking radians here, 0, the output is 0, and we end up at that point. At pi halves, we're at 1. At pi, we're at 0. At 3/2 pi, we're at -1. And at 2 pi, we're again at 0. When we do a horizontal stretch, we're actually affecting the input into the function. So what I'd like to do is look at the graph of y equals sine of 2x. And I want you to notice the input here is 2x. So that 2x represents the angle now. So what I want to do is make another column on here for x on our transform graph. That's our new x values. And note that 2x equals the original angle measure. So our x values for the new graph are the angle measures divided by 2. So here the angle measure is 0, divided by 2 is still 0. Here the angle measure is a half pi, so that would be pi fourths when I divide by 2. Here the angle measure is a half, and when I divide by 2 I get pi halves. Here the angle measure is 3/2 pi. When I divide by 2, x is going to be 3/4 of pi. And at 2 pi, when the angle is 2 pi, my x value is the angle divided by 2, so that's going to be at pi. So notice that at this point now, I get the point 0, 0, so that stays. I've got the point pi fourths comma 1, so I'm over here now at 1. Pi halves comma 0, so at pi halves I'm back here at 0. At 3/4 pi I'm at -1. And at pi, I'm back at 0. So what happens is that graph, when I've done the 2x in there, what I've really done is I managed to fit an entire cycle into a space of pi units on my graph. So the period is now pi instead of 2 pi. In effect, that 2 tells how many cycles fit into a regular 2 pi period, because if I continue on, I'm going to get the graph that looks like this, and I end up with 2 cycles of the red graph in the standard period of the blue graph. Sometimes that's referred to as the frequency, but the more important part is the period. The other thing we need to think about is how do we convert from this multiplier into the period, because remember when we looked at amplitude, the amplitude actually showed up in the equation. The period of pi doesn't show up in this equation. We're looking at things of this form: y equals sine of something times x. That something is not the period, but the period is going to be 2 pi divided by that multiplier. And so that's really how to convert between the period there. So what I'd like to do is look at a couple other examples. Let's try this one: y equals sine of 1/3 x. So if I look at that one, I know my period is going to be 2 pi divided by 1/3, which is 2 pi times 3, which is 6 pi. So now, instead of being in my normal angle and sine of angle here, 0, pi halves pi, 3 halves pi, and 2 pi, now I've got to stretch it out to 6 pi. So I'm going to end up from 0 to 6 pi. I need a whole period. So that would be 3 pi there. This would be 3 times that. That'd be 3 halves pi. And this one would be 9 halves pi. I'm not going to be able to fit this whole thing on the graph, but I can fit some key pieces. That point goes there. The pi halves becomes 3 halves pi. So that one goes to there. The pi goes to 3 pi, which is going to be out here. So I'm going to end up with that first lump is going to look like that much on the graph. It ends up being 3 times as long. The period is now 6 pi instead of 2 pi. We can do the same thing with the cosine graph. I'd like you to try this one with a partner. Y equals cosine of 2x. I'll pause the video for a moment, you pause the video also, and see if you can graph y equals cosine of 2x. So here's the graph of y equals cosine 2x, and again notice that the period is now pi instead of 2 pi. The period is actually half as big as it was before. Let's look at one more example. I want to look at y equals sine of pi thirds of x. I've got the table of values here with our typical things, and again, if I kind of go back here, the new x values are going to be transformed. We're going to start at 0 because I'm not moving the graph around. I'm still going to start at 0, 0. But the question becomes, where does the period end? I know that the period ends when that angle is 2 pi, so I need to find what x is. So I got pi over 3 times x equals 2 pi. So I multiply both sides by 3 divided by pi, and I get x equals 6. So in other words, this period is going to be 6, and so I can fill in the pieces here. Halfway through the period I'm at that point again, and then there and there would be my other x values. So when I go to graph this, I tend to graph the function because I know it's the sine function, and then I just kind of label where things are. That's 6, that's 3, that's 1.5, that's 4.5. We're still at 1 and -1. So that's some basic transformation stuff. You've probably got a handout with some other problems to practice on, so give those a shot. Thanks very much for listening. Have a good day.